Welcome to 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Okay, still on the subject matter of GCE alternative to practical physics. Okay, we have a very important experiment for you. It's on mechanics, but most importantly on relative density. So mechanics, most importantly, or specifically on relative density. Okay, so you must have been looking at the table I have. It looks more than the usual. Okay, so let's get right into it. You must look at the question displaying on your screen. It talks about an object of mass m hung on a spring balance at the pointer position x of the balance is read and the weight in air is determined, and then the weight is then gradually immersed in water. Take note, the weight in air is actually being read on a spring balance. So we're looking at a mass m whose weight is being read on a spring balance in air, and then it is then lowered into water, and also the weight at that point is measured. Obviously, we know that whenever we immerse a mass inside water, we expect it to weigh less. In other words, the loss in weight we are looking when we lower a body into a fluid now is what we call upthrust, simply because the weight of that mass has been displaced off the liquid. But that aside, what we have here is on Roman figure 1. Before Roman figure 1, let me explain more. W1 talks about the weight in air. W2 talks about the weight of the object in water. Okay, this is in air, this is in water, and then this is in a given liquid, of course. So which means if we know the weight of that object as read on a spring balance in air, then the weight in water is expected to be less, and then the weight in liquid is expected to be less, since whenever we immerse a body into a liquid, or let's say water, we expect the mass to be displaced off the liquid, so that it now apparently looks as though the object weighs less at this time. The loss in weight of that object is what we call the upthrust of that object. But let's leave that. The very first question we have on this experiment, it says measure and record the pointer position XYZ, as you can see on the figure on your screen, figure 1. And for that figure 1, it has a scale 1 centimeter to represent. It has a scale 1 centimeter to represent 2 times 10 raised to power minus 2 Newton. In other words, 2 times 10 raised to power minus 2 means 0.02 Newton. So what this means is that for every 1 centimeter, it means 0.02 Newton. Okay, let's leave the scale. Okay, what they want in Roman figure 1 is that we should measure and record the pointer position XYZ. Looking at figure 1, of course, we have only one figure there, figure A, B, and C. A talks about the mass, about the air. B talks about, which is the Y, talks about in water, and C, figure C, talks about, that's Z, talks about the length in a given liquid. Okay, so we were told to measure and record the pointer position XYZ. Now, looking at taking things from the 0 cm mark, x1, x2, x3, x4, x5, x6 is going to give us what we have here as the pointer position. in liquid, in water, for the y1 to y6 is going to give us 1.60 down to 9, 3.10, 4.60, 6.10, 7.50, and 9. Taking reading with our 30 centimeter ruler and measuring things from the 0 cm mark. And of course, the pointer position when in a given liquid, talking about Z, gives us readings from 1.80 to 3.10 down to 10.20. After that, in question 2, we were told to determine the corresponding values W1, W2, and W3. In other words, what that means is that this that we've gotten for X, Y, and Z, we want to convert it into proper weight, not just pointer positions in centimeter. And since we have our scale, that means for every 1 centimeter, that means 0.02. So what this means is 2, because this talks about air, 2 times 0.02. 2 times 0.02, that's going to give me 0.04. 0.04. 3.90 times 0.02, that's going to give me 0.078. In that regard, I can make this to 3 decimal places. Okay. 5.70 times 0.02, I'm going to get 0.114. 0.114. Now 7.50 times 0.02, I'm going to get 0.150 Newton. 9.40 times 0.02, I'm going to get 0.188 Newton. Yes. And 11.30 times 0.02, I'm going to get 0.226 Newton. Okay, that ends that. Now for my Y, that talks about W2. I want to convert this to Newton, to the weight of that mass of the what the weighing balance, the spring balance reads in water. Okay, 1.60 times 0.02. 1.60 times 0.02, that's going to give me 0.032 Newton, and 3.10 times 0.02, that's going to give me 0.062 Newton, and 4.60 times 0.02, that's going to give me 0.092. That's 4.6. 6.10 times 0.02 is going to give me 0.122. 0.122. 7.50 times 0.02, that's going to give me 0.150 Newton. And lastly, 9 times 0.02 is going to give me 0.180 Newton. That is for the weight of the object in water. Now, talking about Z, which talks about my pointer position when the object is immersed in a liquid, I want to try to convert this to Newton now. 1.80 times 0.02, that will give 0.036 Newton, and 3.10 times 0.02, that's going to give me 0.062 as well. 5.20 times 0.02, that's going to give me 0.104, and 6.80 times 0.02, that's going to give me 0.136. 8.50 times 0.02, that's going to give me 0.170, and 10.20 times 0.02, that's going to give me 0.204. Okay, now that we've done that, the next thing is this. Recall that I said when you weigh an object in air, and you take note of the weight, and you lower the weight into a liquid and you try to take the weight, you should know that you're going to experience a loss in weight, a reduction in weight. That reduction in weight is what we call upthrust. In other words, the weight of that object is thrown off water. That loss in weight is what we call upthrust. That's it. So we'll leave that. If you look at question, if you look at okay, that's Roman figure 1, Roman figure 2. In Roman figure 3, in each case, evaluate U equals to W1 minus W2. U equals to W1 minus W2. Telling me W1 minus W2, it means we want to look at the upthrust. We want to look at the loss in weight, W1 minus W2. So 0.040, take out 0.032. 0.40, take out 0.032. That's going to give me 0.008. Yes, 0.008. Now 0.078, take out 0.062. That's going to give me 0.016, 0.016 Newton. Okay, 0.114, take out 0.092. That's going to give me 0.022. Now is 0.150, take out 0.122. 0.150, take out 0.12. Coming for the fourth figure, 0.150, take out 0.122. That's going to give me 0.028. Okay, 0.028. And then to the fifth one, 0.188, take out 0.150. That's going to give me 0.038. 0.038. 0.226, take out 0.180. It's going to give me 0.046. Yes, 0.046. Yeah, 0.046. That's what that means. Okay. Moving on from that, we were also told in Roman figure 3 to look for V. V represents W1 minus W3, which, if you look at it, this is weight in liquid. So you are looking at loss of weight in the liquid, that's upthrust in the liquid. So if you do 0.040, take out 0.036, we have 0.004. Yes, 0.004 to 3 decimal places. Now 0.078, take out 0.062, we are getting 0.016. And then to the next one, 0.114. 0.114, take out 0.104, we are getting 0.010. Yes. And then to the next one, 0.150, take out 0.136, we are getting 0.014. 0.014. And to the fifth one, 0.188, take out 0.170, we are getting 0.018. And lastly, 0.226, take out 0.204, we are getting 0.022. Okay, we've been able to, express all that they've asked us for Roman figure 1 to 3. We were told to tabulate our readings. that we've tabulated already. Moving on to question 5. For question 5, Roman figure 5, we were told to plot a graph of V. Graph of V, which is W1 minus W3 against U, which is U is W1 minus W2. Okay, this is in Newton. This is in Newton as well on the horizontal axis. So in other words, this is going to be my vertical axis and this is going to be my horizontal axis. Okay, so I'm looking at 0.004 to 0.022 that I'm going to have to do justice to. And for these, I'm looking at 0.008 to 0.046. Okay, so the first thing to do is to write the title graph of V, W1 minus W3 in Newton against U. My U is W1 minus W2 in Newton. So that is the graph I want to plot, irrespective of the figures that I have here. You know the deal already. I want to draw my vertical axis and my horizontal axis with a straight unbroken lines. I need to place this very well so that I maximize my score and I do what I can, which is to impress and satisfy what the examiner wants. Okay, so I'm going to also draw my horizontal axis. Okay, okay. So I've been able to do that. So I'm going to put my V in Newton here and my U in Newton here. I'm going to start both from the zero origin. So the next thing is to try to get a very good scale to see how this goes. Okay, I'm looking at the very first figure and I'm thinking 2 centimeter. I'm talking about my V to represent 0.004 because what I have there is 0.04 to 22. So if that be the case, then this would be 0.008 and this would be 0.012, 0.012, and then this is going to be 0.016, and then this will be 0.020, and this will be 0.024. And meanwhile, we stopped at 22. If you are drawing on a paper graph, from here to here is actually a 2 centimeter. It's 2 centimeter. If you're drawing on a graph, I would implore you to use 2 centimeter, like here and here, from here to here, to represent 0.04. So which means 2 centimeter to represent 0.02. So if you're drawing on a paper, from here to here, that's 4 centimeter to represent 0.04, but because I'm drawing on the board and based on the size, that is why I'm using 2 centimeters to represent 0.04. But normally you should be able to use 4 centimeters to represent 0.04 Newton. That said, let's move on. Okay, now to the next thing, my u, I have 0.08 to 0.46. Of course, I'm going to just go direct. Okay, let 2 centimeters be 0.008, and then this will be 0.016, and then this will be 0.024, and then this will be 0.030, and then this will be 0.036. Oh no, we already have a mistake. Oh, this is 32. This is going to be 40, and then this is going to be 0.048. Knowing fully well that we stopped at 46 here, so I've been able to get my graph together. So the next thing I want to do is to write my scale, so I can say, okay, for the V in Newton, for my V in Newton, what I did is 2 centimeters to represent 0.004 Newton. Yes, 0.004 Newton. And then on my U, that's the horizontal axis, 2 centimeters to represent 0.008 Newton. Okay, I've been able to get down my scale. The next thing for me to do is to very quickly pick my point. Okay, now that's a very direct thing. 0.004, 0.008. This is that point. 0.004. When my V is 0.004, my U is 0.008. Now 0.016, 0.016. So I have to try to locate that. Okay, this goes, okay. Okay, rhyming for now. Then 0.010 and 0.022. 0.010. If this is 0.08, in between 1, 2, 3, 4, 5, that should be 0.010. 0.010. Then I have 0.022. This is 16 to 0.024. Okay, I want to look at it. Each of them is 0.008 times 8 times 8, 64. Okay, just before the 8, that's where you're going to have this, just before the 8. So if I trace this up, this is what I'm going to have. Okay, that is not looking all too good. I'm not too convinced about that. Now the next one is 0.014 and 0.028. 0.014 and 0.028. 0.028 should be 0.028. It should be somewhere here. 0.028. No. 28 should be the fifth one. 1, 2, 3, 4, 5. Okay. And 0.014. 1, 2. 1, 4 should be in between. Okay, this is what that looks like. Okay, to the next thing, we still have the fourth one. Yeah, we're still on track. So for the fifth reading now, we have 0.018. If this is 16, 18 should be in between. That's the fifth. So 0.038. 38 should be on the just before the eighth portion, somewhere here. And okay, let me make this look good. 0.038 and 0.018. If this is 16, if I chase that up, that should be the fifth. I'm looking at somewhere here, and that I got that. Now to the last one, 0.022. 22 should be midway before 0.024, and 0.046. 46. This should be 44. 46 should be just before the 8th one, and if I chase that up to the 5th one here, so this is what we have here. We've been able to pick out our points, and what the question now wants is we should determine the slope of the graph. Of course, for you to determine the slope of the graph, out of 6, if you can get 4, then you're good to go. This looks totally way off it, so I'm going to focus on, okay, can I get this point? How many points can I get? Okay, let me make a tweak here so I make this big enough. Okay, trying to pick at least 4 points together. Okay, I'm just going to go with things this way. I'm going to go with things this way. Okay, this is the best I was able to do. Okay, so not too bad. Now to the next thing. After I must have done this, what they want here is I should determine, okay, the slope of the graph. That's on VI. I'm looking for the slope of the graph, VI. Slope of the graph, X. Now the slope of the graph is going to be a change in V in Newton divided by change in U in Newton. Okay, let me try to pick out that slope. Okay, I want to use things I can flow with. Okay, I've been able to do that. Okay, now this represents my change in V in Newton, and this represents my change in U in Newton. Okay, once I've done that, I need to try to get my point, my extrapolation. This falls on 0.08, and this I need to add at least 3 O's to 0.04 T. So if I'm saying 0.008 times 3, that's looking like 0.008 times 3, 0.008 times, no, remain 1 0, 0.0008 times 3. Then I'll add that to 40, 0.0008 times 3. Yes, 3 zeros plus 0.040. I'm getting 0.0424. So this is going to be 0.0424. Okay. And I have my point here. Okay. My extrapolation here is this way. Okay. And then I have another extrapolation somewhere here. So that my change in y looks pretty direct. 0.020, 0.020, take out 0.004, 0.004, all in Newton, divided by 0.0424, 0.0424, take out 0.00, 0.008 in Newton. So the Newton is going to take out Newton. So 0.020, take out 0.020, take out 0.004. You're going to have 0.016. 0.016 divided by 0.0424, take out 0.008. You have 0.034, 0.0344, 0.0344. So this I'm going to divide to get my slope, so that my slope is looking like 0.016 divided by 0.0344, and I'm getting 0.46. I'm getting 0.46. The question saying 0.47 approximately. So my slope is actually 0.47. No unit, because of course Newton had cancelled out Newton. So that's my slope. And if you look at this very well, my V looks like upthrust. Talking about my V, this my V, change in V looks like upthrust in liquid, and this looks like upthrust, loss in weight, upthrust in equal volume of water. So that's what that looks like. This will usher me into the next question, VIIs. What physical quantity does the slope x of the graph represent? What quantity does the slope represent? So when you look at the slope, it's a very simple thing. It represents upthrust in liquid divided by upthrust in water. So if we look at things this way, without much ado, that represents relative density. Yeah, it represents relative density of the liquid. It represents the relative density of the liquid. Okay, so now to the next question. We just finished with VII. VIII, that's Roman figure 8. We were told to talk about precautions we should have taken for if we were to perform this experiment in the laboratory. The first one is to avoid parallax error when taking readings on the spring balance. When we're trying to read the weight on the spring balance, we need to avoid parallax error. If we are measuring on the spring balance, we look at the position vertically, not slanting direction. Also, since if you look at the instruction very well, a certain mass was lowered into water and subsequently into liquid. We must ensure that the mass is not touching the sides or resting on the base of the beaker, as that will distort our results, our readings. So we want to ensure that the mass is not touching the sides or base of the beaker. Another thing, precaution, thirdly, we have to correct zero error on the spring balance. Oftentimes, I'd already explained what zero error is all about. Also, in the sinking the mass into the liquid, we must avoid splashing of water or liquid. That's another error we must avoid. At least it's all part of the setup. If you read things from the beginning of the question, a mass was lowered into water and then subsequently into liquid. So we must avoid splashing. Then we must take repeated readings so that we get accurate results. For accurate results, we must carry out repeated readings. Also, first the mass was dipped into water and then it was removed and then dipped into a liquid. So in bringing out the mass from water first, we must dry it. We must dry it probably with a towel. We must dry the mass before dipping into the liquid. When you look through the set of instructions, it is always very easy to pick out the precautions. So that is on question Roman figure 8, and that ends that question. So to the next question, it says we should define the relative density of a liquid. As you can see on your screen, B1, define the relative density of a liquid. Well, the relative density of a liquid is the ratio of the density of the liquid to the density of equal volume of water. Okay, B1, the relative density of a liquid is the ratio of the density of the liquid to the density of equal volume of water. In other words, RD of liquid equals density of liquid divided by density of equal volume of water. So that is the relative density. That's the relative density of a liquid. Of course, that ends B1. On B2, we were given a certain calculation. A solid has a volume of 30 cm cube and density 2.4 gram per cm cube. If this solid is suspended on a spring balance and half its volume immersed in water, what will be the reading on the spring balance? Okay, there is a way we are going to approach this question, stating all those parameters: volume of 30 cm cube, density of 2.4 gram per cm cube, solid was suspended from a spring balance and only half of its volume immersed in water. What will be the reading on the spring balance? Of course, the mass of the solid, mass of solid, in this case, if you look at all the data that you have there, the mass of the solid, since before now density equals to mass over volume, then mass is going to be density times volume. So the density of this solid here is 2.4 and the volume is 30. So this is going to be 30 times, if we use a mass of solid is going to be density times volume then. So the density is 2.4 gram per cm cube times the volume is 30 cm cube. So multiplying this, we are going to get 72 gram. That is the mass of the solid. Now, since half of this mass was lowered into the liquid, we say of water volume of water displaced. Volume of water displaced, because what that means is that it's more like I have a liquid here and I have a mass here. If I'm putting this mass here, let's say this is the mass before, it's 72 gram. If half of the mass was immersed, you see the part of the mass that occupies this space, then the liquid here is going to come here, to come stay up here, so that this is the liquid displaced. Liquid displaced now. That's the liquid displaced. So volume of water displaced, you're looking at half of 30 cm cube. Yes, because it's only half. So that's 15 cm cube of water. 15 cm cube of water is what was displaced. But recall that the density of water, that's a standard, is 1 gram per cm cube. What that means is that 1 cm cube of water equals 1 gram. So if 15 cm cube of H2O is displaced, then it means it is 15 gram of H2O that is displaced. That's what it means. 15 gram of H2O was displaced. So the volume of liquid displaced is also what we call the volume of liquid displaced is also what we call the upthrust, or the loss in weight, upthrust or loss in weight of the object. So if you're looking at that, so the reading on spring, the reading on the spring balance is now going to be the mass in air, take away the mass of water displaced. Yes, mass of water, mass of liquid displaced. In this case, it was 72 gram. The body was 72 gram. So if 15 cm cube of water has been displaced, it means 15 gram of water has been displaced. Now, the amount of water displaced is the loss in weight of that body. So the loss in weight, or the upthrust, as we call it, is 15 grams. So if we say 72 take away 15, that's going to be 57 gram. Of course, I wasn't told to look for the spring balance will not read in grams, so I have to take this to kg. Taking this to kg will mean 57 over 1000, and that's going to give me 0.057 kg. Of course, my spring balance is going to read in Newton, so to Newton, that's going to be mg, so 0.057 times 10. So that's going to give me 0.57 Newton. So this is what will be my reading on the spring balance. Look through the calculation very well, and of course you will understand what we are talking about. So this is also a probable question. Take that very seriously. So with that, we've come to the end of this question, and I wish you all the best in your GCE Physics alternative to practical, knowing fully well that your practical in physics carries the bulk of the mark for your physics, and for you to get an A or at least a B, you need to do very well in your physics practical. So from myself and every team, everyone on the team here at 300 Plus Academy, it's time to say bye, but do not forget, subscribe to our channel. Like I said, we've not started yet. We are just warming up. We are just about beginning, because your UTME and your other exams preparation I am studying nursing come the next year. This is where you need to be. All you will need for your entrance examination into your various nursing schools. I want to study medicine. I want to study pharmacy, banking and finance, accounting. Just name the course. This is where you need to be for your exams prep, and we can assure you, once you are there to instruction, you are bound to ace your next exam. Don't forget to subscribe, turn on notification bell, and do comment and let us know what you feel. Let us know your concerns. Let us know gray areas where you need more detailed explanation. And of course, you can get that out on our web when you visit 300plusacademy.com, where you get to link up with us on WhatsApp, and of course, exchange ideas with other scholars like you preparing for various exams. And you can anonymously DM us on topics you want us to treat, and we're sure we'll do justice to that. So from me to you, it's bye for now.